Good morning, students. We have learnt the first law of thermodynamics. The heat supplied to a system partly goes in increasing the internal energy and rest of it is utilized in doing the work. So we wrote the equation delta Q. The heat supplied is sum of the change in internal energy and the rest is utilized for doing work. If it is isothermal process, the internal energy remains constant, then internal energy is zero. In isothermal process, U is constant, then delta U is equal to 0. Then entire heat supply is utilized in doing work. This is the equation for isothermal process, where temperature of the system remains constant. Internal energy of the system being constant, it means the temperature of the system remains constant throughout. Now in another process, if pressure is constant, then work done can be calculated as P into D delta V. If P is constant and the volume changes from V1 to V2, then work done can be calculated as I have done it previously, force into displacement. If this is a cylinder and if this is a movable piston, if the piston is pushed upwards, then work is at constant pressure. Suppose pressure is constant here, P is constant. Due to expansion, force is exerted on the piston. As a result, the piston moves upward. When the piston moves upward, the volume changes from V1 to V2. Earlier it was V1, now it becomes V2. So force is multiplied by the distance. Now force is calculated in terms of pressure. Pressure into area of this surface of the piston, surface area of the piston, that gives you pressure into surface area of the piston gives us force into this distance that is moved from initial position to final position. So this A into D gives you the change in volume. This is the change in volume, delta V. So this I can write as P into delta V. It's how we got it in the previous session, if you remember. Therefore, delta W is equal to P delta V, where delta V can be further written as V2 minus V1. So this becomes the equation for the process where the pressure is constant. When the pressure is constant, we call that process as isobaric process. Isobaric process, where pressure is constant. Now the first law of thermodynamics, heat supply delta Q becomes equal to delta U plus P delta V. This is the equation for isobaric process. Now let us solve one example, then you will understand the meaning of this process, that is isobaric process. Delta Q is equal to delta U plus P delta V. Let us solve a problem of calculating change in internal energy. We know from the first law of thermodynamics, change in internal energy can be calculated as delta Q minus delta W. Okay. See the example. Calculate the change in internal energy of 1 gram of water when it goes from liquid phase to vapor phase at 1 atmospheric pressure. Volume of 1 gram of water, we know it is 1 centimeter cube, 1 cc. And volume of 1 gram of water in vapor phase, when it is converted into steam, it has volume of 1671 centimeter cube because of expansion. So volume V2 is 1671 centimeter cube, V1 is 1 centimeter cube, and it is taking place at 1 atmospheric pressure. We know the value of 1 atmospheric pressure. 1 atmospheric pressure is equal to 1.013 into 10 raised to 5 pascals, Newton per meter square. This is already known value. And latent heat of vaporization 2256 joule per gram. In calorie it is 840. In calorie it is 540 calorie per gram. Okay, we are calculating in SI units, so we will not take this second value, we will take joule per gram. So this is the given thing. What is the change in internal energy of 1 gram of water in liquid phase when it is turned into vapor phase at 1 atmospheric pressure? That is, pressure is being kept constant, that is equal to 1 atmospheric pressure. Change in volume is calculated as final volume 1671 centimeter cube. Initial volume of water of 1 gram is 1 cc. With this we can calculate what is the change in internal energy. So here we have the first law of thermodynamics. First law of thermodynamics. We know that delta Q is equal to delta U plus P delta V when pressure is constant. We can say this is isobaric process where the expansion is taking place at 1 atmospheric pressure open to air, right? So delta V is changing volume. So first we will calculate P delta V, which is nothing but work done. Therefore, delta W is equal to P delta V, which is equal to P into V2 minus V1. Here we will take this final volume as V2 and initial volume as V1. So directly we can calculate what is V2 minus V1, and 1 atmospheric pressure can be substituted. 1.013 into 10 raised to 5, right, into 1671 minus 1 V2 minus V1. So this is given in cc, centimeter cube, converted into meter cube. 1 centimeter cube is equal to 10 raised to minus 6 meter cube. 10 raised to minus 6 meter cube. So if you calculate this, this becomes 1.013 into 10 raised to minus 1. So 1.013 into 10 raised to minus 1 into 1670. 1670. This comes out to be 169.2 joules. 169.2 joules. So this becomes work done. Now heat supplied is nothing but latent heat of vaporization. Here delta Q is equal to 2256 joule per gram. This, since we are considering only 1 gram, so we can write heat supplied is equal to 2256 joule. Latent heat of vaporization for 1 gram. So substituting this and this, we will be able to get what is change in internal energy. Therefore, change in internal energy delta U is equal to, using this equation, delta Q minus PdV, P delta V, that is delta Q minus delta W, that is 2256, that is given here, minus 169 0.2 joules. So if you calculate this comes out to be 2086.8. So if you just look at it, when pressure is kept 1 atmospheric pressure constant, when it is expanding, when there is a volume expansion from 1 cc of water to 1671 cc of steam of 1 gram, right? Most part of the heat that is supplied is utilized in increasing the internal energy. Only little part is utilized in doing the work done. That is 169.2 joules of work is being done on the atmosphere, whereas most of the heat supplied out of latent heat 2256, most of the heat supplied, that is about 2087, almost 2087 joule of work is of heat, 2087 joules of heat is utilized in increasing the internal energy. This is the meaning of change of state from liquid to vapor state. Okay, this now will be able to solve the problem using first law of thermodynamics. When a gaseous system is under thermodynamic process, then the pressure, volume, temperature, mass, that is amount of substance, and composition, if it is a mixture of gases, define the state, thermodynamic state of that thermodynamic process. Therefore, the pressure, volume, temperature, mass, and composition, they are called as thermodynamic state variables. Pressure, volume, temperature, mass. Mass is either taken in m or mu. Usually it is amount of substance. Amount of substance is taken in mu, number of moles, mu number of moles. That is mass. And composition. Composition, if it is a mixture of gases. For mixture of gases are called thermodynamic state variables. They describe the thermodynamic process. They describe the thermodynamic process at that particular instant of time. So they are all macroscopic quantities, physical quantities: pressure, volume, temperature, and amount of substance, usually mu. Okay. Now, when a process takes place, then we need to define what is the connection between, what is the relation between pressure, volume, temperature, amount of substance at a particular instant of time. So, the connection or the relation between these state variables is given by an equation that is called as equation of state. The relation connecting the state variables. The relation connecting the state variables for a process, for a thermodynamic equation of state. Equation of state. So you can make them as points. So for an ideal gas, of a fixed mass, for an ideal gas of a fixed mass of given mass, say mu moles. Mass is the amount of substance, say or mu moles of the gas is taken. Then the equation of state for an ideal gas is nothing but ideal gas equation. PV is equal to mu RT. PV is equal to mu RT, which we are already doing. This is called ideal gas equation, ideal gas law, which is obtained, if you remember, using Boyle's law and Charles' law, right? Okay. Now, in this, there are two independent variables and two dependent variables. Totally, there are four variables: P, V, mu, and T, and R is universal gas constant. Universal gas constant. Here, two variables will be either P and V or V and T. I think you got the point. Two dependent variables, you can say two dependent variables, or will be P and V or V and T. For example, if temperature is constant, then the entire right hand side for a given mole of gas, for a fixed mu number of moles of gas, if temperature is constant, then the entire right hand side becomes constant. PV is equal to constant. Then P and V are interdependent variables. P is inversely proportional to V, which is nothing but Boyle's law. Second one, if P is constant, in addition to mu, if P is constant, then we call it as isobaric process, where pressure is constant. Then volume is directly proportional to temperature. If P is constant, mu is constant, then volume is directly proportional to temperature, which is called as Charles' law. So Boyle's law and Charles' law together, we get equation of state, that is for an ideal gas. So equation of state for an ideal gas is ideal gas equation. Okay. Now we will learn some of these thermodynamic processes which you are already knowing. Will just revise what is an isothermal process, what is isobaric process, what is an isochloric process, and what is adiabatic process. Okay. Now we are learning some of the special type of thermodynamic processes, and what are the features. First we will learn isothermal process. Isothermal process is a thermodynamic process wherein temperature of the system remains constant. T is constant. That is, temperature is constant. So throughout the process, the temperature of the gaseous system does not change at all, and you know internal energy also doesn't change. When the internal energy doesn't change, temperature doesn't change. Change in internal energy is zero. So entire heat supplied is utilized for doing work. That is called as isothermal process. Now, if you look at this equation, PV equal to mu RT, right? In this, if temperature is constant, then R is constant and mu for a fixed mass of gas, mu is also constant. The entire product on the right hand side becomes constant. Therefore, PV equal to constant is the state equation for isothermal process. State equation for isothermal process. So from this we can say that P is inversely proportional to V, which is nothing but Boyle's law. Which is nothing but Boyle's law. P is inversely proportional to V. For a given fixed amount of gas, as we increase the pressure, volume decreases. As we decrease the pressure, volume increases. Pressure is inversely proportional to volume when the temperature is kept constant. That is called as Boyle's law. Now second process is isobaric process. Isobaric, bar is always related to pressure. Bar is always related to pressure. So if pressure is constant, if the process takes place with the pressure being kept constant, then it is called as isobaric process. Third one, isothermal process. Isothermal process is the one wherein you see volume is kept constant. Volume is kept constant. Volume of the gaseous system is not allowed to expand. Such a process is called isothermal process. And the fourth one is adiabatic process. As a term itself suggests, adiabatic means where there is no exchange of heat between the system and the surrounding and the system. When there is no exchange of heat, if the thermodynamic process takes place without absorbing the heat or without releasing the heat, then such a process is called as adiabatic process. No exchange of heat. No exchange of heat. A process in which delta Q is 0. No exchange of heat. Then such a process is called as adiabatic process, which can be done by taking the entire gaseous system totally insulated, so that there is no exchange of heat from the system to the surroundings or from the surroundings to the system. Such a process is called as adiabatic process. Adiabatic expansion, adiabatic compression. Isothermal expansion, isothermal compression. Isobaric and isothermic thermodynamic process. Okay. Now we are going to learn mainly two. One is isothermal process and second one is adiabatic process. First we learn isothermal process. Okay. I have written the equation. The equation for isothermal process, PV is equal to constant. This is called as state equation. Equation of the state. Equation of the state when temperature is constant. So P is inversely proportional to V. So if you draw the graph of P versus V, you will get a curve. The curve which is drawn by keeping the temperature constant, P versus V curve is called as isothermal. It is called as isothermal. P is taken along the x-axis, V is taken along y-axis. As P increases, V decreases. Right? As P increases, V decreases. Vice versa. As P decreases, V increases. So this curve is called as isothermal. P versus V graph at constant temperature. When temperature is kept constant, is called isothermal. Isothermal. So as P increases, volume decreases. As P decreases, volume increases. So isothermal expansion means there is a decrease in pressure. There is a decrease in pressure and increase in volume. Isothermal compression means what? There is an increase in pressure, decrease in volume. As pressure increases, volume decreases. As pressure decreases, volume increases. P is inversely proportional to V. Such a process is called as isothermal process. Okay, now we will learn isothermal process and we will calculate the work done in the isothermal process. Let us learn the isothermal process and the work done during this isothermal process. The equation of the state, as I have already written, PV is equal to constant. That is, when P is constant, you will get PV equal to mu RT. Mu is constant, R is constant, so T is also constant. As a result, the entire product mu RT becomes constant. Therefore, PV equal to constant is the equation of state for isothermal process. Now we will calculate work done. Calculation of work done. Suppose a system of gas is undergoing isothermal expansion from P1 V1 initial values to P2 V2 values. From P1 V1 to P2 V2 expansion isothermally. Consider a system of gas which is having initially the state variables like P1 V1 undergoes expansion due to supply of heat. It undergoes expansion from P1 V1 to P2 V2. Okay. Isothermally means without increasing temperature or without decreasing temperature, keeping temperature constant. Then how to calculate work done? Then we know work done can be calculated as, for an intermediate small expansion. When this process is going on, let us consider one small event wherein there is a small expansion dV at pressure P. So what is small amount of work done? For an intermediate step, small work done. Small work done can be calculated as dW is equal to P dV, as we have done earlier. P dV. For that small expansion, we will assume that pressure is constant. For infinitesimal small expansion, for that small intermediate step, we will assume that P is constant for a while. Then we get P dV. Now, if we integrate this, then we will get total work done. Integrating from V1 to V2, we get total work done. Therefore, total work done expansion from V1 to V2. Total work done is calculated as integration of dW, that is integration of PdV, from initial value of volume V1 to final value of volume V2. Initial value of volume V1 to final value of volume V2, PdV. Now we will substitute the value of V from this state equation. We have PV equal to constant. What is constant? Mu RT. PV is equal to mu RT is the state equation. Therefore, what is P from this equation? Therefore, P becomes equal to mu RT divided by V. Mu RT divided by V. So, we can also write P is equal to constant mu RT divided by V. We will substitute this in this equation. When we substitute this, we get integration from V1 to V2, dV as it is, into constant divided by P into constant. So constant is nothing but mu RT. We will take out that constant outside. Therefore, W becomes equal to constant mu RT into dV upon V from V1 to V2. Integration of 1 by x dx. Refer this equation which we have done earlier. Integration of 1 by x dx is equal to natural log of x, natural log x to the base e. In textbook it is also written as ln x. ln x means natural log x, that is log x to the base e. So this equation I can write now, constant into log v, constant into log v to the base e between the definite integrals, upper limit and lower limit. Lower limit is v1, upper limit is v2. Lower limit v1, upper limit v2. Now on simplification, therefore, work done on simplification becomes constant into log v2 upper limit, put the upper limit, log v2 minus log v1 to the base e, natural log. So this can be further written as constant. There is one more very important property of logarithms. Log x minus log y is equal to log x by y. Another one, log x minus log y is equal to log of x by y. This is one of the operations of logarithm. Okay. So this constant times I can write now log of v2 by v1 to the base e. Log of v2 by v1 to the base e. Now what is constant value? Constant value is mu RT. Thus it becomes mu RT times natural log v2 by v1. So this is the equation for work done during isothermal process. Work done during isothermal process. So this work done is positive here. See, V2 is greater than V1, that is during isothermal expansion. During isothermal expansion, what is happening? Volume is increasing from V1 to V2. So during isothermal expansion, when V2 is greater than V1, definitely work done is positive. When work done is positive, then work is done by the system on the surroundings. Work is done by the system on the surroundings, which is positive. During compression, what happens? During isothermal compression, when temperature is kept constant, during isothermal compression, the volume is decreasing from V2 to V1. When the volume is decreasing from V2 to V1, then V2 by V1 will be negative. I mean, work done will be negative. Work done is negative means what? Work is done by the environment on the gas. When the work is done by the environment on the gas, then isothermal compression takes place, work done becomes negative. Because in that case, what is happening? There is a compression. So during isothermal compression, work done is negative. During isothermal expansion, work done is positive. Okay, we will now conclude with the help of heat supply using the first law of thermodynamics. To summarize, from the first law of thermodynamics, we know that heat supply delta Q is equal to change in internal energy plus work done. So for an isothermal process, delta U is equal to 0 because entire heat supply is utilized for doing work, since change in internal energy is 0. So delta Q is equal to delta W. So entire heat supply is equal to work done. Therefore, what happens? Whatever the equation for work done we got, that is now become mu RT. That becomes mu RT log V2 by V1 to the base E. So this is the work done, right? When heat is supplied, when heat is supplied, when heat is supplied to the system, to the gaseous system, Q is positive, work done is also positive. Then what happens? Since heat is supplied, work done is positive. Since V2 is greater than V1. So this is the equation for isothermal expansion. So isothermal expansion, work done is positive. Therefore, on absorbing heat from the surroundings, on absorbing heat from the source, the system does work on the surroundings. By the system work is done by the system on the surroundings. By undergoing expansion. So this is called as isothermal expansion. Isothermal expansion. When final volume is smaller than the initial volume, final volume is smaller than the initial volume, means if the volume is decreased during isothermal compression, then what happens? This becomes negative. This becomes negative. V2 will be smaller than V1. So when V2 is smaller than V1, then work done is negative. During isothermal compression, we can conclude work done is negative. work done is negative because final volume is smaller than initial volume. Final volume is less than initial volume. That is the meaning of isothermal compression. Work done is negative. When work done is negative, then Q is also negative. This implies Q is also negative. Means this implies during isothermal compression, heat is released. Heat is released to the surrounding. These are the features of isothermal expansion and isothermal compression. This is isothermal expansion. This is isothermal expansion, and this is isothermal compression. During isothermal expansion, work is done by the system on the surrounding. Therefore, it is positive. So Q is also positive. That is, heat is absorbed by the system. On absorbing heat from the system, the entire heat absorbed is converted into work done on the surrounding. Whereas in the second case, what happens? On compression, isothermal compression. During isothermal compression, when temperature is constant, during isothermal compression, the volume is decreased from higher value to smaller value. As a result, work done is negative on the system. Work done is negative on the system means work is done by the surroundings. Work is done by the surroundings on the system. As a result, work done is negative. Heat is also negative. Heat is negative means what? Heat is released to the surroundings. So these are the two features of isothermal expansion and isothermal compression. In the next video, we will learn about adiabatic process. Adiabatic expansion and adiabatic compression. Thank you. Have a nice day.